Arjun, we've touched on attention before in case TCM0033005, but today we're tackling the big one, the transformer. What made it such a game changer?
It's about scale and speed. Before the transformer, processing long sequences was a bottleneck. This paper offered a radical simplification that unlocked new possibilities.
The authors themselves state that dominant sequence transduction models are based on complex recurrent or convolutional neural networks in an encoder-decoder configuration. These were the workhorses of NLP. Exactly. While these models did have attention, the best-performing models also connect the encoder and decoder through an attention mechanism. It was an add-on, a clever way to help RNNs.
So attention wasn't new, but its role was limited. It was like a spotlight helping the RNN focus, but the RNN was still doing the heavy lifting sequentially, one step after another. This analogy highlights attention's role in highlighting importance, but it breaks because attention isn't a passive light, it actively blends information.
But then came the core idea. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
Dispensing with recurrence and convolutions entirely? That feels like throwing out the engine and just keeping the headlights. This analogy captures the radical shift in perspective, but it breaks because RNNs and CNNs were highly effective engines for their time. The transformer just introduced a different, more parallelizable architecture.
It means instead of processing words one after another or through fixed-size windows, every word can directly interact with every other word at the same time, weighing their importance.
So, no more waiting for the previous word's output? Every word gets to see every other word simultaneously? That sounds like an explosion of connections.
And that explosion of connections is precisely what makes it more parallelizable and requiring significantly less time to train. This is the big advantage.
So the all you need in the title really refers to parallel processing being enabled by attention, not just better quality. That's a key shift from how we thought about attention in hashtag TCM 0033005.
The results spoke for themselves. The transformer achieves 28.4 Blue score on the WMT 2014 English to German translation task, significantly outperforming prior state-of-the-art models.
And Blue score is a standard metric for machine translation quality, right? So it wasn't just faster, it was demonstrably better too. Efficiency and quality.
Yes, a clear leap forward. Now, how does this attention-only architecture actually work? We need to peel back the layers and see the transformer's internal machinery.
Okay, so we know what it achieved and why it was needed. Let's see the high-level picture of how it uses attention to replace recurrence and convolution.
Let's start simple, visualizing the model as a single black box. In machine translation, input a sentence in one language, get an output in another.
Like translating "Hello World" to "Hola Mundo." The transformer takes the whole phrase, not just word by word, and gives the whole translation.
Correct. And inside that black box, we find two main parts, an encoding component, a decoding component, and connections between them.
An encoder to understand the input sentence and a decoder to generate the output. This is a common pattern in sequence-to-sequence models.
Yes, but with a twist. The encoding component is a stack of encoders. The original paper used 6, stacked one after another.
So it's not just one pass. The input gets processed through multiple layers of understanding, refining its representation as it goes up the stack.
Exactly. Each encoder itself has two key sublayers. First, the encoder's inputs first flow through a self-attention layer.
Self-attention. That's where each word looks at other words in the same input sentence to understand its context, right? Like it in the animal ate it.
Precisely. The outputs of that self-attention layer are then fed to a feed-forward neural network. This is a standard neural network layer.
So self-attention gets the context, and the feed-forward network processes that context independently for each word. But how does this enable parallelization?
That's the critical insight. While self-attention has dependencies to calculate those contextual weights, the feed-forward layer does not have those dependencies.
Meaning each word's processing through the feed-forward network can happen completely in parallel with every other word's. That's where the speed comes from.
This leads to a key property. The word in each position flows through its own path in the encoder. No waiting for the previous word.
So the transformer treats all words in the input as a set, not a sequence, for much of its processing. It's like a batch operation for meaning. This analogy highlights the simultaneous processing, but remember that the self-attention layer still creates dependencies to compute its weighted averages, even if the subsequent feed-forward network processes each token independently.
To begin, as is the case in NLP applications in general, we begin by turning each input word into a vector using an embedding algorithm.
Standard practice, but crucial. Words become numerical representations that the network can work with. And we also need to account for word order, which we covered in hashtag TCM093003.
Exactly. We add positional encodings to these embeddings. Now we have an input ready for the first self-attention layer. But how does this self-attention actually calculate those contextual weights?
Okay, so the high-level structure makes sense. Stocks of encoders, each with self-attention and feed-forward. Now let's get into the mechanics of self-attention itself.
Consider the sentence, "The animal didn't cross the street because it was too tired." To understand it, a human knows it refers to animal.
And when the model is processing the word it, self-attention allows it to associate it with animal. That's its purpose, resolving ambiguity by looking at context.
To do this, for each input word's embedding, we create 3 vectors from each of the encoder's input vectors. These are called query, key, and value.
Q, K, V. These sound like database terms. Is there an analogy there, Arjun? Like querying a database for relevant information?
It's a perfect analogy. Think of it like this. The query vector is what you're looking for, the key vectors are what you're trying to match against, and the value vectors are the actual information you want to retrieve. This comparison holds well for matching and retrieval, but it differs from a typical database lookup because you're not just retrieving one item. You're blending all value vectors based on their key's similarity to the query.
So for each word, its query asks what context is relevant to me, its key says, here's what I offer as context, and its value is, here's my actual meaning.
Precisely. The next step, calculate a score by taking the dot product of the query vector with the key vector of every other word.
A dot product measures similarity, so we're asking how much each word's query matches every other word's key, how relevant they are to each other.
These scores are then scaled by dividing them by the square root of the key vector's dimension, often written as the square root of dk, and passed through a softmax operation. This scaling helps stabilize gradients during training, and softmax normalizes them so they become weights that sum to 1.
So now we have a set of probabilities for each word, indicating how much attention to pay to every other word in this sequence. It's a distribution of importance.
Yes, this softmax score determines how much each word will be expressed at this position. It's a learned interpolation, not a hard lookup.
Ah, in case number TCM0033005, we introduced attention as a lookup mechanism. Now, with the transformer, it's clearly a learned interpolation or weighted average that combines information dynamically.
The final step is to multiply each value vector by the softmax score and then sum them up. This combines the actual information, values, weighted by their relevance, softmax scores.
So the output of self-attention for a word is a blend of all the other words' meanings, weighted by how relevant they are to the current word's query.
For it, in our example, its query vector would have a high dot product with animals key vector. That high score, once softmaxed, means animals value vector gets heavily weighted when we sum up the weighted value vectors.
And street's value vector would be almost ignored. This perfectly explains how the model associates words.
This whole process we just described is for a single attention head, but the transformer actually uses multi-headed attention. The paper notes that the choice of smaller query key and value dimensions is partly to make the computation of multi-headed attention mostly constant.
Multi-headed? So instead of just one QKV process, the model runs several in parallel, each learning different kinds of relevance. What's the benefit?
Exactly. The original paper states, multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. One head might focus on syntactic relationships, another on semantic connections, and so on.
So it's like having several experts, each with a different lens, analyzing the context simultaneously, and then somehow their insights are combined?
Precisely. The outputs from each attention head are then concatenated and linearly transformed, allowing the model to decide how to weigh and combine these diverse perspectives into a single, richer contextual representation.
That makes sense. More angles of attention for a more complete picture. So that covers the encoder's sophisticated self-attention. What about the decoder?
The decoder is also a stack of layers, but each has 3 attention sublayers. The first is a masked self-attention layer. Unlike the encoder, the decoder's self-attention is masked to ensure that predictions for a token only depend on known outputs, simulating unidirectional generation.
So for generating text, it can't cheat by looking at future words, maintaining that autoregressive property. This aligns with the unidirectional generation in our mental model.
Correct. And then there's a second attention layer, an attention layer that helps the decoder focus on relevant parts of the input sentence.
So this is where the decoder looks back at the encoder's comprehensive output to decide which parts of the source sentence are most important for generating the next word.
Precisely. This combination of masked self-attention and cross-attention is what allows the decoder to generate coherent, contextually appropriate output, step by step, while still leveraging parallel processing for each step. It's a beautifully engineered system. But even a breakthrough architecture like the transformer has its inherent limits.
Limits? After all this talk of parallelization and unprecedented power, what could possibly be a weakness of the transformer?
While revolutionary, no architecture is without its trade-offs. The transformer, despite its more parallelizable and requiring significantly less time to train nature for many tasks, does face challenges, especially with very long sequences.
Long sequences? You mean like entire books or extensive conversations? I thought the whole point was to handle long-range dependencies better.
It does, but at a cost. The self-attention mechanism, where every word interacts with every other word, results in a computational complexity that scales quadratically with sequence length. For an input of n tokens, the calculations are roughly proportional to n squared.
N squared for attention? So for short sentences, that's fine. But for extremely long documents, that N can make the training and even inference times explode, requiring immense memory and compute.
Exactly. That quadratic scaling is a major bottleneck. Furthermore, the positional encodings we discussed earlier, while crucial for order, are typically learned for a fixed maximum sequence length. This means the size of this list is hyperparameter we can set. Basically, it would be the length of the longest sentence in our training dataset. Exceeding this trained length can lead to poor performance.
So if I train a transformer on paragraphs, it might struggle with a whole research paper because it hasn't seen positional patterns that far out or simply can't process it efficiently.
Precisely. The architecture, while powerful, has inductive biases. While the original paper boasted that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data, it also specifically stated the transformer outperforms the Google Neural Machine Translation model in specific tasks. This implies specific contexts of optimal performance.
So even the all-you-need transformer isn't a magic bullet for every single language task or scale. Understanding these boundaries is as important as understanding its core mechanism, especially as we push towards even larger models.
Absolutely. Recognizing these limitations has driven subsequent innovations like sparse attention mechanisms or architectural modifications to address quadratic complexity and expand context windows. But that's a story for another case file.
Another powerful case closed, Arjun. The transformer truly revolutionized NLP, not just with its capabilities, but by also laying the groundwork for how we think about scale and efficiency in attention-based models. And thanks to you, I feel like I understand its engine and its speed limits.